Okay, I just got the message that is being recorded. Okay, so let me start by thanking you for the invitation. It would have been nice to actually come in person to San Diego, but as Javier was saying, my personal circumstances at the moment don't allow. So apologies for that, but hopefully maybe in the future. So today I'd like to tell you a little bit about this work that I've done in collaboration with Benjamin Withers from the University of Southampton, which appeared late last year, so in November, on the topic of nonlinear response in real-time holography. And I know that some of you are working on real-time holography, so hopefully this talk will be somewhat useful to you. So in this talk today, I'll be interested in retarded response in strongly coupled relativistic quantum field theories, and I'll be thinking about finite temperature. And the most obvious observable within this class of observables is simply the retarded two-point function. So here I denote such a retarded two-point function as GRA, and some of you might already be familiar with the RA notation. But for the rest, I'll explain that in a couple of slides. So this retarded two-point function is, as the name suggests, it's a function of 2 points, x1 and x2. These are the 2 points where I do the operator insertions in my quantum field theory. And if, say, we want to compute the retarded two-point function of an operator O, then this quantity will be given by what I have here on the right-hand side. So in order to compute it, we need to take the operator O at position x1, take the commutator of that with the operator at position x2, then take the thermal expectation value of that commutator and then multiply the whole thing with this theta function here, which essentially says that x1 has to be in the future of x2. Now, just from this definition, it's not too difficult to see where this function has support. And in particular, it turns out that this two-point function is only non-zero when x1 lies in the future light cone of point x2. So if x1 and x2 were space-like separated, then this commutator would have been 0. And if x1 was in the past of x2, then this theta function would have been 0. So crucially, this retarded two-point function is only non-zero when x1 is in the causal future of point x2. And now this is quite important because it essentially tells us that this quantity here is intrinsically non-Euclidean. And it's non-Euclidean because it depends crucially. Sorry, was there a question?
No, no sé café.
So, sorry. So this quantity depends crucially on the time ordering of the 2 points. And because of precisely this reason, it poses a little bit of a challenge to standard holography. In order to really compute it, we need to move into the realm of real-time holography. So, but since this point is quite important, let me elaborate a little bit more on it. So essentially, standard holography is this statement that I summarize here. So it says that the partition function of the quantum field theory is actually equivalent with a string theory path integral approximated by evaluating it on a gravitational saddle point. And then the sources on the quantum field theory essentially become boundary conditions that we need to impose on our fields in the bulk. Now, this statement alone, as is very well suited for Euclidean problems, but it's not enough when we want to do things, when we want to compute observables that are non-Euclidean. And the reason is that it doesn't tell us what to do with the state of the quantum field theory, or equivalently, it doesn't tell us what to do with initial data in the bulk. So say, just to drive the message home a little bit further, let's say that we want to compute the simplest thing, a retarded two-point function of a scalar operator. Then in the bulk, what we need to do is we need to consider a scalar field and essentially solve the Klein-Gordon equation, subject to boundary conditions, according to this standard holographic prescription. But this is not enough to fix our the observable of interest, because how are we going to do a time evolution in the bulk if we don't know what initial conditions to consider? Okay. So bottom line, the standard holography is very well suited for Euclidean problems, but not for the calculations we have in mind. And at this stage, you probably are quite puzzled because such retarded two-point functions have been extensively studied in the literature. So how does that connect with what I just told you? And it turns out that historically, the computation of two-point functions within holography didn't pose any problems because people were very clever and they came up with a prescription that actually gives the right results. And this prescription is usually referred to as the Skenderis-van prescription, and it was published in these two papers in collaboration with Herzog as well, and essentially says that the extra thing that one needs to do is to impose not only boundary conditions in the UV part of our bulk, but we also need to impose ingoing boundary conditions at the horizon of the black hole that sets the temperature of the quantum field theory we are interested in. Okay, so this is the extra ingredient that one needs to consider in order to be able to fully fix the observable that we are interested in this case, the two-point function. Now, this prescription, this Skenderis prescription, not only gave the correct result for this retarded two-point function, but that actually also gave rise to a very beautiful result that essentially connected this linear response with the ring down, the black hole ring down. And to be more precise, essentially what Skenderis found was that this retarded two-point function actually has simple poles precisely at the locations of the black hole quasi-normal mode frequencies. So this is a very beautiful and quite universal result. However, this prescription is quite unsatisfactory from the perspective of the quantum field theory. And the reason it's unsatisfactory is that we're doing a mixture of things. We are imposing boundary conditions in the UV, and those we know how to interpret from the perspective of the quantum field theory, but we're also doing something at the horizon of the black hole. And that is not clear how to interpret from the quantum field theory point of view. And in order to understand this connection, where does this ingoing boundary conditions come from? We need to go into the realm of real-time holography. So essentially, real-time holography is a prescription. It's an extension of the standard ADS-CFT dictionary that tells us how to deal with Lorentzian observables. And one such prescription came from Skenderis-van Rees in 2008. And if we start with this prescription, one can actually prove explicitly that for two-point functions, you can derive this ingoing boundary condition at the horizon. And I'll show this later on in the talk.
Christiana?
Yes.
So what's wrong? I always thought also that ingoing boundary conditions is the same as regularity conditions if you go to the infalling infalling coordinates. Yeah.
Yes. So you would expect, and I'm not going to argue with that, you would expect ingoing boundary conditions to be the result of causality, which is essentially what you're saying is regularity at the horizon. But yeah, we just wanted to prove it.
Yeah.
Okay. That's an expectation. So we wanted something more solid than an expectation.
Okay, good.
Okay. So as I said on my title slide, I want to go to the nonlinear level. So I want to go beyond the retarded two-point functions that I was just telling you about. And in particular, I want to study 3-point functions. Now, a 3-point function, a retarded 3-point function. Now, I denote such a retarded 3-point function by GRAA. And in this case, it's a function of 3 points, x1, x2, and x3. In order to compute this quantity, if, say, we have an operator O, we need to compute these two terms. So let's start with the first term first. So we take the operator O at position x1, commutator with the operator position x2, and then we take the nested commutator of that with the operator at position x3. Then we take the thermal expectation value, and then we multiply with these two theta functions now that essentially say that x1 is in the future of x2 and x2 is in the future of x3. So that's the first term. And then the second term is essentially the same, but with x2 and x3 exchanged. Now, just we did before, let's try to understand where this function has support. So it's not too difficult to see that this first term is essentially non-zero when x1 is in the future light cone of x2 and x2 is in the future light cone of x3. And similarly, the second term is non-zero when x1 is in the future light cone of x3 now, and x3 is in the future light cone of x2. So essentially the ordering between x2 and x3 doesn't really matter as long as x1 is in the future light cone of both of them. So in terms of the actual computation that one needs to do in the bulk, so now we have to solve something that is non-linear. And in order to do that, we need to specify what sort of interactions we are going to consider. So if we go back to the example that I gave earlier of having a scalar operator, so say we want to compute the 3-point function of a scalar operator, then in the bulk, we need to consider, once again, a scalar field, but now we need to specify what interactions we'll consider for that scalar field. And the simplest thing to do, and this is what we're going to do today, is to consider a lambda phi to the cube term. So at this stage, it's in principle not clear whether we can use the Sons-Darnet's prescription of ingoing boundary conditions. So our approach will be to start from scratch, not assume anything, start from real-time holography, following the prescription of Skenderis-van Rees, and actually explicitly derive that one can use ingoing boundary conditions. Okay. So having said all this, let me just summarize what the motivation of this talk is, or if you want, what we want to achieve by doing this calculation. So I think, given the audience, it's clear to everyone that holography is a very powerful tool for studying strongly coupled quantum field theories at real time. To date, this real-time aspect hasn't been explored fully. So in this talk, we are trying to partially extend the framework itself a little bit, and then use that framework to actually compute some observables. And in particular, we'll be computing the retarded 3-point functions of a scalar operator. And in the meantime, we will also answer these two questions that I wrote down here. Firstly, we want to check whether we can impose simple ingoing boundary conditions for higher point functions. So we know already that at the level of 2-point functions, so within the linear regime, that is true. That's what Starnet's, Son and Starnet's proposed, and that was essentially proven in a way by Skenderis and Van Rees. So that's one thing we want to do. And another thing, we want to check whether this universality between black hole ring down and correlation functions, higher point correlation functions, whether extends beyond the level of 2-point functions. Okay. So these are the two questions that we want to answer. Now, there is another sort of tangential motivation, and I'm not going to say much more about this other than what I have here on the slide. So another motivation for studying these nonlinearities actually comes from waveforms from black hole mergers and the observation of gravitational waves from the LIGO collaboration a few years ago. So as you know, if you have a black hole merger, if you wait long enough after the merger, then the black hole will be described by a Kerr configuration plus the longest lived quasi-normal mode. But if you want to actually fit the waveform closer and closer to the actual merger, you need to consider nonlinearities. Now, surprisingly, this hasn't been done. There is quite a bit of work currently, but this is far from being understood. Now, what we're doing is not in flat space, it's in asymptotically ADS, but the advantage of actually doing the computation in ADS first is that we are essentially allowing the quantum field theory to systematize these nonlinearities for us. And then once we understand that, we can extract the knowledge we got and apply it in the asymptotically flat space-time case. Now, I won't be saying much more other than this along these lines. So are there any questions before I move on to the next part of the talk?
It's all clear.
Excellent. Okay, so first, I wanted to, just to make sure that everyone is on the same page, I wanted to give a brief review of real-time holography a la Skenderis-van Rees. So, as I said several times already, we want to compute correlation functions at finite temperature. In order to do this computation, our starting point is essentially to write down a generating function that when you vary it with respect to the sources, you get the correlation functions that you want. So that's our starting point. Now, when we're doing things in real-time holography, when we are writing down this generating function, we need to go into the Swinker-Keltish formalism. So according to this formalism, we are considering a quantum field theory that lives on a closed complex time contour. So we're not considering a quantum field theory in Euclidean time. We are not considering a quantum field theory on Lorentzian time. Instead, we're considering a quantum field theory that lives on this closed contour that is complex in time. Okay. So let me walk you through this complex contour. It looks something like this. So in particular, it has 3 segments. It has 2 Lorentzian segments and 1 Euclidean segment. So the first Lorentzian segment is segment 1, is this blue segment here. So it's parameterized by time t1 that flows forward in time from time 0 to some final time tf. Then we have segment 2 that is also Lorentzian and it flows backwards in time and is parameterized by time t2 that goes from t final down to t equal 0. And then we have a third segment that is now Euclidean and it's parameterized by this Euclidean time tau. Now, these 2 red dots here essentially indicate that those 2 points on the contour are identified. So instead of a Euclidean segment, we have, in fact, a Euclidean circle. And the period of the circle is given by beta. And beta is inversely proportional to the temperature of the quantum field theory that we are considering. Now, essentially, what the purpose of this Euclidean circle is to prepare the state of the quantum field theory. Okay, and the simplest way to say this is by doing a time evolution along this Euclidean segment. So in order to do that, what one has to do is to insert an operator that is e to the minus beta h, but that is precisely the density matrix of the theory. Okay, so the Euclidean circle just prepares the state for us. And in what follows, I will do operator insertions on the 2 Euclidean segments, but not on the, on 2 Lorentzian segments, but not on the Euclidean segment. So whenever I insert an operator on segment 1, I will call it O1, and the corresponding source will be J1. And if I insert something on segment 2, I will call that O2 and the corresponding source J2. Now, you might be wondering about this T final. So T final doesn't really matter as long as it's big enough so that all the insertions that I want to do fit in the contour. Okay. Now, for convenience, it will turn out to be better for us in doing this calculation, instead of considering O1 and O2, to do a slight change of bases and consider OA and OR instead. So OA is essentially the difference of the two operators, and OR is the average of the two. And then the corresponding sources, essentially JA is again the difference between the two sources, and JR is the average of the two. Okay, and this is the AR notation that I used earlier. Those indices were referring to these quantities here. Now, with this at hand, we can go and we can write down the quantum field theory path integral. And that is now a function of the two sources that we have, JA and JR. And it looks something like this. Okay. And let me point out that this TP here is the contour ordering operator. And once we have this at hand, then it's pretty simple to compute the endpoint correlation functions. Essentially, you just vary this quantity with respect to the sources n times, and then you get the endpoint correlation function just like what you see here. So just as an example, if we vary this quantity with respect to JA twice, we'll get GRR, which is usually referred to as the symmetric two-point function. And it's not too difficult to see that this will essentially be the thermal expectation value of the anti-commutator of the two operators. If instead we do, again, two variations, once with respect to JA and once with respect to JR, depending on the order, we will either get the retarded two-point function, GRA, or the advanced one, GAR. And both of these are essentially given by the commutator of the two operators. And essentially, they are, as you would expect, related by time reversal. And last but not least, if we take two variations with respect to JR, we get GAA, which turns out to be trivially zero. So within this AR formulas, not only we get the retarded two-point functions, but we actually get them in a form of a bigger matrix. In the case of two-point functions, this is a 2x2 matrix with 4 components. Now, out of the 4 components, not all of them are independent. And in particular, if we also take into account the fluctuation dissipation theorem, it turns out that only one component is independent. And usually we take that to be GRA, so the retarded two-point function. Now, if instead of varying this partition function twice, if we vary it 3 times, we'll get a 3x3 now matrix of 3-point functions. So that matrix will have 9 components, but of course, out of all those 9 components, not all of them are independent. And if we take into account the fluctuation dissipation theorem, there are only 3 independent ones. So these are usually taken to be GRAA, GARA, and GAAR. So in this talk, we'll be computing only one of those, and in particular, the GRAA, so the retarded one. Okay, and of course, but if you vary this generating function more than 3 times, you get bigger matrices for higher point correlation functions. Okay, so and here is precisely where the power of holography kicks in, because it essentially gives us a way to compute this partition function from the gravity side. Okay. So for the observables that we want to compute, once again, we want to do things within real-time holography. So we have the quantum field theory that lives on this Swinger-Keltish contour. So when we go and compute the string theory path integral, we essentially approximate it by evaluating it on a saddle point once again, but that saddle point has to be dual now to this Swinger-Keltish contour. Okay, and this is precisely what Skenderis-van Rees did in their paper in 2008. They put forward a proposal for what the gravitational saddle is for this Swinger-Keltish contour. And according to their prescription, the geometry that we need to consider in the bulk essentially has 3 pieces, each piece corresponding to one of the 3 pieces on the Swinger-Keltish contour. Okay, so if you want, they took this Swinger-Keltish contour and they filled it in towards the bulk in the following way. So for the Lorentzian segments, they filled that in with a Lorentzian black hole. For example, this segment corresponds to this piece here. Then this other Lorentzian segment corresponds to another segment of a Lorentzian black hole, which looks like this. And then finally, the Euclidean circle was filled in with a Euclidean black hole, which is essentially a Euclidean cigar, and it's what you see here. Now, of course, that's not enough. They also proposed that these 3 segments actually have to be piecewise smooth. So when you join them, you need to impose that the geometry has to be piecewise smooth and C1 at the joints. Okay. So essentially, when you want to do computations that are non-Euclidean, you need to consider your fields, your gravity calculations being done on a geometry like this, instead of the standard Schwarzschild that we usually consider. In this case, the proper thing to do is to consider this geometry that is piecewise. And this will be our starting point for the computation of the retarded 3-point functions of our scalar operator. Okay. Are there any questions here?
Oh, yeah, Christiana, where is the boundary in this geometry?
Well, it's here. Yeah. I mean, here I'm just essentially suppressing the x1, x2 if you're in 4 dimensions. So you can think of this as your r, and this is the time, and I'm suppressing the other 2.
I'm wondering in this picture, I mean, I understood that was the bulk. So I was trying to draw the horizon radius, the horizon.
Actually, yes, that is a very good question. The horizon is somewhere here.
It would be that it's not that the 0, the origin.
So it's, I mean, here, yes.
Yeah.
But as you go up, it's not actually included in your geometry. So if you think in terms of the Penrose diagram of ADS, you have your horizons at 45 degrees.
Right.
But this line here corresponds to a constant r that is outside the horizon.
So you're not drawing the whole bulk, or is it just a problem of the drawing, or?
No, it's not a problem of the drawing. So it's just the geometry doesn't reach the horizon.
And what stops it from reaching the horizon? I mean,
you can go as close as you want, but this
is not a hard wall or something like that.
No, it's not. Yes, that's the prescription. You can go, you can consider R being, so when you join these 2 segments, you can join them, you join them at a constant radius slice on the Penrose
Yes.
diagram, and that can be as close as you want it to the horizon.
So the boundary dips into the bulk. So it's, I mean, these T1 and T2 curves, there you say they're reaching inside the bulk to some finite radius surface. So they're leaving the boundary or something like that, or
No.
No, so just think of this as a piece of a Schwarzschild in the simplest case, that's a piece of a Schwarzschild black hole. So in ADS, so you have T1 is, as I draw it here, is the boundary of that ADS black hole, or the segment of that ADS black hole. And then you just don't reach the horizon. You go up to a certain radius in the bulk, but not all the way.
Yeah, that I understood. What worries me is that this curve seems to be reaching the boundary. I mean, this curvy thing, this bent curve at the back, this is a constant radius.
Yes.
And it's reaching the boundary because it merges with T1 and T2. I mean, it's merging with the color curves, which are the boundary.
Yes. That if you think about it in terms of the Penrose diagram, there is it's okay.
Okay, I see what you mean. I see what you mean. It's is this at future infinity where they are joining or something like that?
It's yeah. So
okay. Right.
the further you go close to the horizon, the further in the future. So T final is further away.
Okay. No, thanks.
So I have another question. So is this prescription different from the one of these guys, Glorioso and Liu?
Yes, that is actually a very good question. And as you see, as you will see on my very last slide for the outlook, we don't actually understand how the two are related to each other. I don't think even
if I understood this in this paper, they enter the horizon and get out, right?
Yeah, but it's not just that, it's the whole approach is completely different. So they're even the starting point, they consider an effective field theory approach to non-equilibrium. And in principle, that they don't need even a partition function for doing that calculation. So it's a completely different approach, and they don't even themselves agree whether they agree or disagree.
Okay, good.
Yes. So, yeah, it would be very good to understand how the two prescriptions are related to each other, and it would even be good to understand how results using the two prescriptions compare. So when we put out this paper, I think a couple of in the same week, there was another paper that was computing pretty much the same thing using the other approach. And we just haven't been able to even compare our results with those, just because the formula is so different. That's not to say that it can't be done, but at least we haven't done it. But yeah, no, that is an excellent point.
Christiana, one further question. What happens at the joins? It's enough to have the C1 condition that you pose there to avoid the, I don't know, some stress energy condition.
It seems to be. And I'll show precisely where this conditions on the joins become important, and you'll see that it's actually precisely what you need. But also, this is not to say that there are no other saddle points. I would say that that is an open question. They proposed one such saddle, and it turns out that it works. But nothing stops you from coming up with a different saddle and do the calculation there, as long as you asymptote to the Singer-Keltisch contour and you get the right result. but now maybe it would be a complex geometry. I don't know. That could be something. But yeah, this is most certainly not the only option. Well, it's the only thing that people have considered in the literature. But there might be other things. Anything else?
No.
Okay. And just to add on that, now complex geometries are quite fashionable, so maybe one could try that. Okay, so this is essentially a summary of the Skenderis-van Rees approach for real-time holography, and this is essentially what we'll be using in what is to come in the talk today. And essentially, as I said already, we want to compute the retarded 3-point function of the scalar operator. In order to do that, we'll essentially be considering a scalar field living on this geometry. Okay, so that will be our starting point. So let me just jump right in and show you how the ingoing boundary conditions at the horizon come from this real-time perspective. So in the bulk, we will be considering a massive scalar field. And since we want to do things at the nonlinear level, we need to specify what interactions we'll be considering. And in particular, we'll be considering the simplest thing, which is lambda phi cube. Okay. And so if there are absolutely no sources on the quantum field theory, then the thermal expectation value of the operator O dual to the scalar field will be equal to 0. Okay. And then the profile of the scalar field itself in the bulk will be everywhere 0 on all 3 segments. Now, let's say that we want to introduce sources on our boundary theory. And in particular, let me introduce a source J1 on segment 1, a source J2 on segment 2, and let me take them to be equal to each other. If they're equal to each other, they will also be equal to JR, and JA, which is the difference, will be 0. And now let me take this JR to be perturbatively small. Okay. Just because of these sources on the boundary, this will essentially force the scalar field to be non-zero at order epsilon. Okay. So, and I know this by psi, and this will essentially control the 2-point function. But having psi non-zero, because of the interaction term that we introduce, this will source a term at order epsilon squared. And I denote that by chi, and chi will essentially control the 3-point function, etc., etc. If I wanted to compute 4-point functions and above, I would have had to consider higher order terms here, but for the purpose of this talk, I don't need to consider anything else. Now, of course, we also have the metric, and we need to worry whether we need to include any back reaction. But it turns out that at the order we are interested in, we don't need to include any such back reaction. So we consider our geometry just simply being what Skenderis-van Rees told us to be. Okay, so we'll have the simplest case, 2 segments of a Schwarzschild black hole plus the Euclidean cigar. Okay, and then we plug this sort of ansatz in our equation of motion for the scalar field, and we'll get 2 boundary value problems, one at order 1 and one at order 2. Now, given that the geometry itself is piecewise, it makes sense to consider the scalar field, or if you want psi and chi, as being piecewise as well. So we have psi 1, psi 2, and psi e, and similarly, we have chi 1, chi 2, and chi 3. So at order 1, for all our psi...
I'm confused.
Yes.
So these forces are valued in the boundary, so there are fields in the boundary. Or so
So these are the boundary conditions that you need to impose when you solve for your scalar field in the bulk.
Yeah, so these are okay, yeah. Okay, then
Yeah, so if you want your scalar field psi to asymptote to something that is non-zero on the boundary, then for sure it will have a non-trivial profile in the bulk. And then if you have something that is non-trivial at order epsilon, then simply because of the interactions, you have to have a term at order epsilon square. Is that better?
So these sources are completely general, could be time dependent, or could be anything at this point, or
These fields, psi and chi, in principle, yes.
or well, or the sources J1 and J2.
Yeah, I suppose that could be whatever you want. We are picking them to be constant.
So you're rewriting your bulk scalar field as the sum of two other bulk scalar fields.
Yes.
So what's exactly the way you split it? You have a parameter epsilon, and then you have...
So when I introduce the sources on the boundary, I take those sources to be very small. I took them to be perturbative.
So this epsilon is the parameter that controls the back reaction. That
yeah, essentially, if you want, yeah.
Okay.
So essentially, what I'm doing, I'm trying to do a perturbation around equilibrium. This is what epsilon is. Is the parameter controlling how far I am from equilibrium. And my equilibrium state has this VEV of the scalar operator being 0.
So you say that psi controls the 2-point function. So is there an explicit dictionary? You extract it from the boundary, or how does it?
If you give me maybe
okay.
5 slides time, I'll show you explicitly. But in principle, just if you don't consider this expansion, so in order to get the 2-point function, what you need to do is you need to get the expectation value of this operator here and essentially divide it by the sources, right? That's the standard way we compute 2-point functions in holography. Now, this will introduce sources at order epsilon. So we need to compute the expectation value of this operator at order epsilon square. At order epsilon, and then divide that with the source epsilon in order to get the 2-point function. So psi is what controls the VEV of phi at order epsilon. So that's why it controls the 2-point function. Now for the 3-point function, we need to know the VEV of the scalar operator at order epsilon square, and then we divide by the source twice.
I see.
So, but I'll give the expressions later on, so hopefully it will be more clear. Anything else? No? Okay. So I have this ansatz, and I plug it in the equations of motion for phi, and I get 2 boundary value problems, which I write down here. So at order 1, I have this Gleim-Gordon equation essentially for every component of my scalar field psi. And then I have these boundary conditions. So psi 1, remember, is the field on segment 1, and it should asymptote to source J1. On segment 2, it should asymptote psi 2 should asymptote to source J2, and we have no sources on the Euclidean segment, so psi E should asymptote to 0. So this is at order 1, and then at order 2, we need to solve this equation here, which crucially has a right-hand side. And this is essentially the statement that order epsilon sources the field at order 2. Okay, that's precisely what I meant. And now in this case, we want all the segments of the scalar field chi to go to 0. This is because we want to measure the response of the system at order 2, given sources at order 1. Okay, and of course, on top of this, we need to impose match conditions between the various segments. Okay, so let me start by explicitly showing you how to solve this first boundary value problem, and then we'll look at the second one later on. Okay, so our strategy will be the following. We will start by considering a single delta function on the boundary of one of the segments, say segment 1. And then we'll measure the influence of that delta function on all 3 segments. And in order to measure that influence, we will essentially be considering bulk to boundary propagators. Then we will repeat the same thing, but now considering a single delta function on the boundary of the other segment. And then essentially what you do is you superimpose the 2, and you get something that has a source both here and here. Okay, so that's the strategy. So let's start by considering a delta function on the boundary of one of the 2 segments, say there. Then the bulk to boundary propagators will look something like this. So we have delta 1, 1, delta 2, 1, and delta E1. The second index denotes where on which segment the delta function source lives. And the first index shows where on which segment we are measuring the influence. Okay. And in all 3 cases, we can expand this bulk to boundary propagator in terms of the retarded and advanced bulk propagators in this way, with some unknown constants CR and CA for each of these 3 bulk to boundary propagators. Okay. And so we have 6 undetermined constants that we need to fix. And it turns out that we have precisely 6 conditions that we need to impose. These 6 conditions, 3 of them come by imposing boundary conditions. Okay. So for example, here we have a delta function on segment 1. So C11R plus C11A should be equal to 1. Well, on segment 2, we don't have any source. So C21R plus C21A should be equal to 0. And same for the Euclidean segment. So these are the boundary conditions, and they give us 3 algebraic relations. And then, as there was a question earlier, we also need to impose the matching conditions between the segments. And these matching conditions, we have 1 match condition there, 1 here, and 1 here. So we have 3 more relations. So we have precisely 6 unknowns and 6 conditions, so we can solve explicitly for CRA. Okay, so this is for the delta function on the boundary of segment 1, and then we repeat the exact same process now for the delta function being on the boundary of segment 2. And if we do all that, then we can go and compute the total field on each of the segments. So for example, if we want to compute the total field on segment 1, what we need to do is we need to have delta 11 J1 plus delta 12 J2. So we convolve the bulk to boundary propagators with the sources. That's what we're doing. But remember, J1 and J2 are equal and equal to JR. So we can take JR as a common factor out of the parentheses, and then we have delta 11 plus delta 12. So if we plug in the precise expressions that we have for these coefficients CR and CA, what we find is that this quantity here is only dependent on GR, so on the retarded bulk propagator. Okay. And if we do the same for the total field on segment 2, we'll find again something that only depends on the retarded GR function. And if we also do the same for the psi E, so the field psi that lives on the Euclidean segment, we'll see that it's trivial everywhere. So what happens here is actually very interesting. So you put in the delta function there, it influences the future and it influences the past as well. The influence towards the past goes through the segment, through the matching point here, through the joint, into the Euclidean segment. Then it comes all the way around, it crosses through the other joint, and it cancels out precisely with the influence of the other delta function towards the past. Okay, and in such a way that the influence towards the past and along the Euclidean segment completely cancels out. Okay, so what we see here is that the response to the system is purely causal. It only goes towards the future. Okay, and the prescription of Son and Starnes essentially is just the statement. You can, instead of considering this three-piece geometry, you can just simply consider this slice here, this one single Lorentzian segment, and then impose ingoing boundary conditions at the horizon. It's because of this essentially magic cancellation that this prescription works. So this is at the level of 2-point functions. Now we want to ask whether we can apply this to the level of 3-point functions. So essentially what we need to do is we need to go and solve the second boundary value problem. And the approach is essentially exactly the same as we just did. Now the difference is that now our sources, if you remember the equation that we need to solve, the sources are because of the non-trivial scalar field psi that lives in the bulk. So in this case, our sources are not in the boundary, they're instead in the bulk. So we'll start by considering a delta function in the bulk of one of the segments. And then instead of considering bulk to boundary propagators, now we'll consider bulk to bulk propagators. We'll compute all these coefficients Ci and Cr. And then we put the delta function source in the bulk of the other section. We repeat the same, and then we convolve with the sources. So if we want to find the total field chi on segment 1, because of sources both on both of these segments, what we have is here. We have delta 1, 1 convolved with psi 1, that's on segment 1, plus delta 1, 2 convolved with psi 2 square on segment 2. But now psi 1 and psi 2 are identical to each other, just like what we had before. So we can take them out as a common factor, and we have here delta 1r, which, just like before, only depends on the retarded part. So the evolution is once again causal. It goes towards the future. Okay? And precisely for that reason, we are allowed to consider just one single segment, one single Lorentzian segment, and impose ingoing boundary conditions at the horizon. Now, if we want to go to order 4, it's not clear, at least to me, how this will work. Because here it's crucial that psi 1 square and psi 2 square are the same. Yes, so at this stage, we have proven that we can impose ingoing boundary conditions in order to compute the retarded 3-point functions. We haven't actually computed the 3-point functions, okay? Because we haven't done any of these integrals explicitly. And it turns out, I mean, it's quite obvious that it's simpler to actually take advantage of the fact that we can impose ingoing boundary conditions and do the calculation the standard way instead of doing these integrals. And this is what I'll do in the next part of the talk. Are there any questions before I move on? Hopefully I haven't lost everyone. Okay, so let me continue. So as I just said, we want to do the calculation since we know we are allowed to do the calculation by imposing ingoing boundary conditions. We'll take advantage of that. So we'll be considering here a single Lorentzian black hole spacetime, and we'll be solving the two boundary value problems that we saw before for psi and for chi on this geometry. Now, for convenience, we'll be doing this calculation in momentum space. So instead of considering GRAA, we'll be considering the momentum space version of it, which we denote as R3. And R3 is now a function of two momenta, P1 and P2. Okay. And just like before, we need to solve the equation for psi and chi. Remember, now we have just one single segment. So there are no, these fields are not piecewise anymore. Okay. So in order to solve the equations for these two scalars, we start by introducing this sort of ansatz. So in particular, we take our scalar field psi and we decompose it in plane waves. Okay. So in particular, we have one mode with momentum P1. We call that psi1. And then we have another mode, psi2, which has momentum P2. And here I also explicit S1 and S2 as the amplitudes of the two modes, just for later convenience. Now, if you have this at order epsilon, then this will source the scalar field at order 2. So it will source the scalar field at order, the scalar field chi. And in particular, you'll have three modes now. You'll have one mode, chi11, that carries momentum 2p1. You'll have another mode, chi22, which carries momentum 2 times p2. And then you'll have a third mode, chi12, that carries momentum p1 plus p2 with the appropriate explicit S1 and S2 factors. Now, for the calculation that we want to do, which is compute the 3-point functions, this chi11 and this chi2 are just coming along for the ride. They will not be in any way useful to us. Okay, so for all practical purposes, you can just forget about them. Okay, and then so we need to solve this for these fields psi1, psi2, and chi12, subject to boundary conditions in the UV and ingoing boundary conditions at the horizon. So let's see what boundary conditions we impose in the UV. So for our scalar field psi, psi1 and psi2, we impose that we want to have a source term. But remember, we've already explicit the amplitude of these modes here. So the source we can set to 1. And then we also have a vev that is psi I, and it appears at the appropriate order given the mass of the scalar field we're considering. And then for the field chi12, we impose that we do not want to have a source. That's because we want to measure the response of the system at that order. But it will have a vev, and the vev is given by chi12 delta. So this goes back to Javier's question. So the 2-point function in momentum space will be essentially given by the vev psi1 delta. And the 3-point function will essentially be given by the vev chi ij delta. That's essentially because we've already set the sources to 1. So if you want, it would have been chi12 delta over whatever you had here, S1 and S2. Yeah. Is there a question?
Yeah, no.
Yeah, okay. Yeah, okay. So the goal is to go and do our numerics and compute these two quantities, because these two quantities essentially give us what we want, the 2-point function and the 3-point function. And in order to do the numerics, you need to fix the details of the theory. So in particular, we fix delta equal to 4. We fix the scaling dimension to be 5/2 for no obvious reason, and just the value we picked. And the amplitude of the nonlinear interactions, remember we have lambda phi cube interactions, we've set lambda to be 1. And for simplicity, we did this calculation at 0 spatial momentum. Okay, so this is the calculation that we did. But before I move on to show you the results that we got, let me start by describing what sort of singularities we expect to see in this 3-point function. So when we thinking in terms of singularities, it's useful to think in terms of contact diagrams. Remember, we are doing lambda phi cube, so at 3 level, the contact diagrams look something like this. So P1 and P2 are the momenta of the ingoing modes. And then because of momentum conservation, the third leg, the outgoing, should have momentum P1 and P2. So we expect to have singularities in our 3-point function when at least one of these legs corresponds to Quadrant mode. So we can have single poles when one of the 3 is equal to Quadrant mode. We can have double poles when 2 of them are equal to Quadrant mode. Or in principle, if the kinematics of the theory allow, we can have even triple poles when all 3 legs are Quadrant modes. Okay, so this is what we expect to see. And just a bit of notation. I mean, we have too many parameters, so we can't plot everything explicitly. So in terms of parameterizing things in terms of P1 and P2, so the ingoing momenta, we thought it was more useful to parameterize things in terms of P and S. So P is the total momentum, and S is the difference of the 2 ingoing momenta. Okay, and in the plots that I'll show you on the next slide, we essentially fix S to some value, and then I'll be plotting this retarded 3-point function on the complex P plane. Okay. So this is it. This is the main result of the paper, if you want. So here I'm plotting the real part of the retarded 3-point function of a scalar operator on the complex P plane. And you see several poles, all of them in the lower complex plane. And all these poles are single poles. And as you see, I've marked some of them with circles and some of them with crosses. This is because the mechanism that gives rise to them is different. And let me be more explicit. So the circles corresponds to what we call resonant quasi-normal modes. So the outgoing leg is the one that corresponds to a quasi-normal mode. So P1 and P2 conspire in such a way that they resonate, and the outgoing leg is a quasi-normal mode. Now, we also have the crosses. The crosses correspond to the scenario where one of the ingoing legs corresponds to a quasi-normal mode. Okay, so just the contact diagrams look something like this. So this is for a generic value of S. Now, if we fix S to something very specific, so if we fine-tune it quite a bit, then as you can imagine, some of these poles can collide, and you can have higher order poles. Okay, so the simplest one to see is when S is equal to 0. So when S is equal to 0, then this cross and this cross will meet, and you would expect to see an order 2 pole. And this is precisely what I'm drawing here. So this is essentially, if you want, the same plot as before, but now for S equal to 0. And here I'm only plotting positive values for P, the real part of P. And indeed, we see that we have a second order pole. And just as I was just telling you about, in this case, we have both of the ingoing legs corresponding to quasi-normal modes. Now, if you fine tune S to a different value, and in particular to something that looks like this, you can have a circle and a cross from the previous diagram colliding, okay? And this is what we see here. Again, this is a second order pole. And in this case, we have one of the ingoing legs and the outgoing leg being quasi-normal modes, okay? So this is poles of order 2 for very special fine-tuned values of S. Now, the question is, can we see poles of order 3? And the answer is that in our specific model, the model that we looked at, we couldn't find any such poles. Now, this doesn't mean that if you pick a different model with different interactions or a different scaling dimension, you wouldn't find any. It's just the kinematics of the model that we consider did not allow for order 3 poles. So that's one statement. And the other statement, which is actually important, is that we couldn't find any other poles beyond the poles that I just discussed. So all the poles that we saw had some connection with quasi-normal modes. There was nothing that appeared out of thin air. And this is a result in itself. So we see here that the result that Son and Starnitz had about the relationship between linear response and black hole ring down actually continues to 3-point functions. Now, for 4-point functions, we don't know. And the reason we don't know is that there you can have loops in your contact diagram. So it's not clear whether those will contribute to anything or not. Okay. So this is are there? Oh, I've gone over time. Yeah, I'll be very quick. So we got a couple of extra things. We managed to get a 3-point function of the stress energy tensor and 2 scalar operators for free, essentially, by solving the word identities. And we got that 3-point function in terms of the 2-point functions of the scalar field. And that can extend to higher point functions. That was one free result. And another free thing that we got is we actually saw that the fluctuation anticipation theorem for 2-point functions is precisely manifest in the bulk-to-boundary propagators. So if you express your field psi and psi r in terms of JA and JR, and you use the coefficients JR and JA that we found, then you get that the bulk-to-boundary propagators in this basis, they look something like this. And delta RR is essentially precisely the same as the fluctuation anticipation theorem. And this begs the question whether we can understand the generalized fluctuation anticipation theorem in this way as well. Okay. And with that, let me summarize and conclude. So here I've discussed retarded 3-point functions, thermal 3-point functions for scalar operator. And I also told you, I didn't show you, that we can also get another 3-point function containing the stress tensor for free. We've shown that at least at the level of 3-point functions, we can use ingoing boundary conditions on a single sheet. And we also shown that the universality between black hole ring down and nonlinear response does exist. And we only saw single and double poles in what we did. Now, in terms of the future, there are a few things that we're working on with Ben. One is to compute the other 2 3-point functions, the other 2 independent components of the 3-point functions. So GARA and GAAR. We also want to understand the generalized fluctuation anticipation theorem from the bulk in terms of the bulk-to-boundary propagators, if possible. Another direction we are exploring is the 3-point function, the retarded 3-point function, now of only stress tensors. And as Alfonso was asking earlier, we want to understand the relationship between the Skenderis-van Rees approach and the Crossley-Glorioso-U prescription. Currently, we don't understand that, and I don't think it's clear in the literature either. And we want to connect with results that use that formalism. And with that, let me finish here and apologize for running so late.
Okay, so thank you.
Thank you.
Yeah, so we are way over time. There's one question. Well, just one quick question. It seems like, I mean, your formalism also applies to, you don't need a temperature, do you, actually?
Well, the contour would be different.
But you can extend it to 0 temperature.
I mean, there are, yeah, there are other contours that people have considered, and the Skenderis-van Rees approach also considered the original Skenderis-van Rees paper did consider other contours like the in-out contour, and some people have used it, and some other contours that, yeah, in principle, it can be used.
Well, so thank you very much again. We're starving, so.
Yes, sorry, I should have been more considerate.
So nice to see you.
Yes, as always.
Thank you very much. We have two. What?
Detener la grabación.
Ah,
Antes,